So I'd like to introduce the next, our keynote speaker, Professor Stephen Chu from Stanford University. Steve is the Kennan Professor of Physics, Molecular and Cellular Physiology, and of Energy Science. Truly a polymathic combination of disciplines. He's going to be talking to us today about the role of materials and nanotechnology in getting to net zero greenhouse gas emissions. And I'll just note that Steve has had a long and distinguished career beginning as a researcher, independent researcher at Bell Labs, where he conducted work on optical trapping and cooling that was recognized with the Nobel Prize in 1997. In physics, notably also, in addition to his distinguished scientific career, has been his incredible service to the United States and to the world in a number of different capacities. First, from 2004 to 2009 as the director of Lawrence Berkeley Laboratory, where he really set an ambitious energy agenda for the energy transformation. And then from 2009 to 2013, where he served as U.S. Secretary of Energy under the President Barack Obama. And some of the institutions that we now in the research community take for granted were things that he created under his term as secretary. ARPA-E, the Advanced Research Projects Energy, the Energy Innovation Hubs, like our own Liquid Sunlight Alliance here at Caltech, and the Clean Energy Ministerial. And he was the first scientist cabinet member, and so really set blazed a trail there. But of course we also have a deadline. We have a deadline associated with the need to mitigate the seemingly insurmountable challenges associated with climate change. And so he's going to be telling us about the role of nanoscience and nanotechnology and the role of materials in getting to net zero greenhouse gas emissions. I don't know if there's going to be a time axis associated with that, but I look forward to, and I invite you to join me in welcoming Professor Stephen Chu.
Well, it's a pleasure to be here today to talk about something I care a lot about, and I hope you all too. And so first, set the vocabulary. And what's the difference between climate and weather? And the answer is climate is what we expect and weather is what we get. So climate is a long-term average, averaged over decades, seasons of local weather. And what was happening, it's since record from 1850 to January 2004 is that the temperature, the average temperature of the Earth has increased. The UN goal of staying below 1.5 degrees is being passed. So January was 1.6, but the average will go within a year or two. And so let's look at what's causing this. If you look at the historical record, the amount of emissions from greenhouse gases, CO2, methane, nitrous oxide, over the last 2,000 years was pretty flat, and then it just suddenly started to take off at the beginning of the Industrial Revolution. Not all greenhouse gases are the same. Carbon dioxide is oversaturated, meaning that if you put on more greenhouse gas, there's 5-fold absorptions of carbon dioxide, the wings get broader. So we're saved because it's oversaturated, but methane and nitrous oxide are not. And so methane is 84 times worse than carbon dioxide, but it gets oxidized in roughly 10 years. Nitrous oxide, very different, 300 times worse and stays around for 100 years. Carbon dioxide, we're not sure how long it stays, but thousands of years. All right, what else do we know about this? N2Os and methane is particularly worrisome because it's very intimately tied with agriculture. Roughly half of the methane is from agriculture, food production, and more than 75% of N2O is from fertilizer. Why do we think it's due to humans? Well, you can do modeling and you can take out the rise of the greenhouse gases and you find that the temperature should not have changed, and the black curve is the observed temperature rise and the brown fuzz is the uncertainty. I should also say it's not just the counting of the amount of greenhouse gases. There is a dead giveaway that this time it's different. The climate has changed in the past before. We've gone through series of ice ages, warming periods, ice ages. And the smoking gun is that you look at the carbon 12 to carbon 14 ratio. Carbon 14 is made in the upper atmosphere. And you have cosmic rays making neutrons. The neutrons then turn nitrogen into carbon 14. It's radioactive, diffuses down. We all have carbon 14 in ourselves. And the carbon 14 has a lifetime of 5,700 years. We use carbon 14 for dating. But imagine taking you, suppose you die, you're sequestered from the biosphere, and thousands, not thousands, but hundreds of thousands, million years later, we exhume you and use you to power a fossil fuel plant. You have no more carbon 14 in you. It's all decayed. And so the dilution of carbon 14 to carbon 12 also fits quantitatively with this. So it had to have been sequestered carbon. And so this is why this, because if you look at the history in the past, the temperature goes up, the CO2 goes up. What was leading, what was lagging. But this is different. Because if you look at the carbon cycles on Earth and in the oceans, on Earth it's much faster than 5,000 years. Trees grow, they die, and they get recycled. So that's the evidence that this is a different climate change. This is now with these models, you can predict what possibly could happen. We're here, and so we're somewhere between no climate policies and current policies. And the current policies might end up at 3 degrees centigrade in this century. And so I also want to note that if you want to say below 1.5 and 2 degrees, the total greenhouse gas emission has to go to 0. And that's a problem, going to 0. The other thing I should remind you of is that what we've done to the atmosphere already is not visible. The oceans are cold. Anyone who's done snorkeling or scuba diving know this. Very slow mixing of the surface temperature to 1 and 2 kilometers deep. And it will take 50, perhaps 75 years for it to come to equilibrium. So it's like you have a glass and you got ice cubes, and the glass stays cold because the ice cubes have this heat reservoir. And so as we measure more of the oceans using buoys that goes down 2 kilometers and go up approximately 1 degree everywhere in the oceans, we're finding, yes, most of the heat is slowly heating up the oceans. So it's as if you were smoking cigarettes for the first, from your 20s until your 40s. You decide it's bad for you, you stop, but there's a time delay. And so that's another problem, because you can't just say, well, I'm going to be really sure the climate's changing, so we'll just wait a little bit longer. Okay, there's a built-in thing here. Okay, it's okay. So as you well know, the multiple industrial and agricultural revolutions really transformed the world, but there were unintended consequences like greenhouse gas emissions. And I'm here to tell you about what we need in another industrial and agricultural revolution. And this is going to be really essential. And so it's partially history, and all know that those who cannot remember the past are condemned to repeat it. But I prefer Gay and Wilson's philosophy. There's a soothsayer, a concerned woman looking at a crystal ball, and the fortune teller says, "You will make the same foolish mistakes you have made before, not only once, but many, many, many times again." So it's good to know about history. Okay, history. First Industrial Revolution, improvement of the steam engine of Newcomb by James Watt, and huge transition from animal and human power to iron horsepower and fossil fuels. It's also a materials issue. By then you had these things, but there was another materials issue because you have iron and you wanted steel. And the first great steel process was developed by Bessemer during the Crimean War. This was a war where Russia invaded Crimea and Europe said, you know, we don't want you to do this. It's the same mistake over and over again. And the irony was the explosives that propelled the shells were getting better and better, and the cast iron things would blow apart. So he developed a method of making steel. Let me talk about a few other revolutions that we all know about and are fond of. Big deal, the invention of the transistor. First, the point contact transistor by Bardeen and Bertin, and not Shockley. Those two were in Shockley's department when they made this transistor, and they're the people on the patent. Shockley got really, I use the technical term, pissed about this. And so, you know, how dare they invent something without me? So he holed up in a conference. He was a brilliant theoretical physicist, and he holed up in a conference, and for the next couple of days, he actually wrote the foundations of semiconductor physics, and in that he also invented p-n junction theory and p transistors. And shortly thereafter, Thiel and Sparks made the same thing at Bell Labs. What people don't realize is you needed high purity materials, because once you had high purity materials, you can dope what you needed to do. And so there were two people, starting with Bill Fan at Bell Labs, who invented zone refining. So you have a hunk of germanium, and then you have a thing you melt and let it refreeze, and you get back and forth, and you push the impurities out. And also Thiel and Sparks adopted a method invented years ago to make single crystal, first in germanium, then silicon. I have to tell you a very quick story. I'm new kid at Bell Labs. There's this, next to me, there's this office, there's this old guy, totters in, goes in, kind of goes around, and he disappears. A few people come visit him. After a couple hours, he leaves. I said, who's this guy? And my department says, you don't know who he is? No, he's Bill Fan. Who's Bill Fan? And he says, this reminds me of a story. There are these two young cavemen. And there's this old guy walking by, and one guy says, who's he? You don't know who he is? He invented the wheel. And the other guy says, yeah, but what has he done lately? And so my department head ends with the story. He invented zone refining that made transistors possible. He gets to do whatever he wants to do. And so it was that transformation of being able to dope. Optical communication. The ability to make really pure fibers was the key to optical fiber communication. And so it's really critical. And I'll show you a few more examples of materials that really allowed these revolutions to occur. But let's talk about energy, climate change, greenhouse gases. So this is from an IPCC report of where the stuff comes from, transportation, agriculture, so you can read it yourself. And so remember, we got to go to zero in everything, which means you got to go to zero in all these sectors. And that means the elimination of emissions from steel, concrete, plastics, chemicals, and textiles. It's not just getting rid of fossil fuel for electricity production. You got to get rid of all the greenhouse gas emissions from the entire food chain, which is about a quarter, if you include food waste as well. So that's a big deal. And then we have to develop a different philosophy. In the last 50 plus years, we have all these things, use once, throw away. I'm not just talking about paper bags and plastic bags and shopping things. I'm talking about a lot of things. We build buildings, commercial buildings, and we typically tear them down in, let's say, 50 years. Of those buildings that we build, China maybe 40 years, Europe maybe a few hundred years. Nothing's recyclable except the steel, nothing else. And so how do we actually build buildings that last a long time? And so the goal is to reuse, not recycle. Now, some good news. The price of renewable energy has plummeted. This is the price of solar modules starting in 1976 to 2019. On the y-axis is cost. It starts at $100 per watt. That means $100 you can buy a solar cell that generates a watt of electricity at a standard sun. And now it's about 3 cents. So, and this was 99.6, now 99.7.5%. It was like ridiculous. More recently, this is just modules, but you're really concerned about the total cost of the energy, the so-called balance of systems. But even here in this graph, from 2010 to 2019, solar drops from $378 per megawatt hour to $68. And so offshore wind, onshore wind plunging. Okay, all good news. Nuclear energy skyrocketing. This is a little out of date, it doubled again, starting with 3 Mile Island. So the price of nuclear was going down, down, down. 3 Mile Island happened, and around the world, it just went through the roof. Coal, roughly the same, and so, okay. So good progress, but if you have renewable energy, it's not a turn-on source, and so you need some additional innovations. All right, and so let's talk a little bit about what we need in this next industrial revolution. The good news is possibly solar is going to improve, but in addition to that, we need the backup power generation capacity, energy storage, enhanced transmission distribution systems, things like that. So I'm saying that these renewable energy sources have to be less by about a factor of 2 because all this other stuff matters. When it's 10 to 20 or 30% of the energy, you have it, right? But when it's 50, 60, 80%, you don't. And California is now 70% carbon-free electricity, of which 10% is nuclear. And as we go to more and more renewables like solar, energy storage becomes a key issue. And in noontime in the summer, we're now beginning to warm up the ground with solar energy. Okay, so this is an issue. And as I said before, you need to decarbonize things. In the solar energy, possibly we have a new kid on the block, perovskites, a new type of material. Perovskites with silicon or different mixtures of perovskites can make a multiple layer of photocells. Very high efficiency, very high progress. This is, for example, perovskite solar cells, fast learning curve. A couple years ago, they would only last a couple of months. Most recently, 2 groups this year have reported 15-year estimated lifetime based on accelerated lifetime testing. You get to 25 years and you're in the pink because these could be cheaper. Solar, silicon solar is about 30 years. So that's good. Electricity. In the past, we would generate electricity locally, use it locally. Edison made the first electrical plant in New York City, but he wanted to he wanted electricity to use light bulbs. There was a competition between Tesla/Westinghouse and Edison. Edison wanted DC and Tesla wanted AC because Tesla thought with AC you could up the voltage and send it over longer distances. Totally different now because if you look at, for example, solar resources around the world, lots of rich solar resources, but in many places that's not where the people are. That's both good and bad. There are no people, land is cheap, you can have solar, but you want to get it to where the people are. As an example, let's blow up Europe and Northern Africa, the Middle East, and you see tremendous solar resources. I want to point out Germany. Germany's over here, about the same color as the state of Washington around Seattle. And yet, solar works in Germany. So people are dreaming of transmitting across, for example, coupling using high voltage DC lines from the hydro resources in Norway and the renewable resources from Iceland to the continent. You need DC because this is underwater, and so the AC coupling to the water is not good. So it has to be DC, and and you need high voltage DC, which means it's a materials problem. Better dielectrics mean you can go to higher voltage. The power transmitted, the resistive loss scales as V squared over R. Double the voltage, you quadruple the capacity. And there's, you know, these are plans or under construction. This is just a plan. High voltage DC, China leads the world, and they are now installing 12 gigawatt DC lines, and you can go over 2,000 miles, 5% loss. Very good, but very big. Those are people. And that's the high voltage standoff. Okay? As I said, higher voltages is good. It's not only, you know, the high voltage towers, it's the transformers. That's a transformer at 1.1 megavolts, and those are people. Okay, what about the wires conducting them? Copper weighs too much, so they use aluminum, but aluminum doesn't have enough strength, so they have a steel core that supports them. So you want a very strong wire that goes over longer distances to have fewer of those towers. And they're beginning to think about and beginning to design carbon composites as a core because it's lighter and stronger. And so let's talk about these materials and needs. And for the first thing you want to do is step back and say, well, if you're going to talk about materials and resources, what do we got? What does the Earth supply us with, the Earth's crust? And this is an interesting plot of the materials we use in humans use on Earth. This is the annual world production in metric tons. It's on a log graph, so these are powers of 10. And what do you see leading the way? Well, there's concrete, followed very closely by oil, coal, natural gas. Of all the stuff in the world, fossil fuel is the biggest mass of stuff if you add up that stuff, okay? And then steel next. And there's one thing, this is, remember, orders of magnitude and non-fuel wood, so wood for construction. Then down here are the other things we use, like aluminum, copper, zinc, lead. Over here, these blue things, that's plastics. But plastics, the feedstock is petrochemicals, oil, and now natural gas. So of all the stuff we use, it turns out fossil fuel is a major component of the world's by weight, okay? So in any case, this carbon is an interesting thing because remember they were using steel as the thing for the transmission lines, but if you go to carbon fibers, then you can have higher tensile strength by factors of 3, 4, 5, a little higher conductivity, but you use the aluminum for the conductivity, and here's what you have in terms of tensile strength of conductors, and aluminum's over here. Why is this nice? This is nice because this shows, this is research from Matteo Pasquale from Rice, and he is turning methane gas into carbon fiber. Why is this nice? Because we anticipate there will be a copper shortage within 50 years, 100 years, if you electrify. And so can you actually, and I have to stress, we have unlimited sources of carbon under the ground. So if you can bring it up as natural gas and turn it into something that's useful that will displace construction material, that would be great. But before that, you can do higher value things. What's the conductivity possibility? Well, if you have nanotubes that you can get to link and percolate well, then it's well better than any metal conductor. So can you replace metal as conductors? It's all about money. Okay, let me tell you another thing that we have to think about, and this is a wide bandgap semiconductor electronics. It started in electronics with germanium, small bandgap, went to silicon, bigger bandgap. It's great, so it had better properties. But if you go to wider bandgap materials, like silicon carbide, you have lots of improvements. In power electronics, you wire bandgap semiconductors to reduce power losses, converting AC to DC for the DC transmission lines. So what you're doing is you're turning whatever electricity you have for high frequency AC and boost it up and turn it back to DC. And so with this, it would be great. And so on Secretary of Energy, we decided that the people making the converters or inverters or whatever will never make fundamental materials research. They're going to be users. And so we started actually funding companies to make higher quality wide bandgap semiconductor materials, notably silicon carbide and gallium nitride. Diamond would be great, but no one's how to figure out how to get a PMP transistor for diamond. So those are some of the things we need. And the advantage of having a scientist start at the UE is you can actually identify problems that would not be funded by industry, which is a good application. All right, let's talk more about electronics. This chart was made around 2015, and in 2015, you have how the electronics is being used. This is so-called ICT, so this is information communications technology. Blue is the networks, wireless networks. Red is production of the materials used in the industry. The yellow is consumer devices, computers, televisions, mobile phones. Widescreen TV this big is a couple hundred watts. And so and these are data centers. So what is projected to happen is that as we use more and more compute power, and especially with artificial intelligence and machine learning, the compute appetite is insatiable. A long time ago, there was a feeling, how much is good enough? But with machine learning, it's off the charts. And so as you project to 2030, there's a projection that says maybe this is the amount of data centers. The TVs might get a little more efficient, but people may not start with the big screens. They end up looking at the iPads, and with you have young, good eyeballs, you can get enough joy out of an iPhone, but whatever, and networks, okay? So this is a problem. So you need, how much energy do we use now in electronics for this information, compute, and communications? 5 to 8%. And so it could double or triple. And so we fundamentally need a better approach to electronics. As electronics get smaller and smaller and smaller, the design rule is now 2 nanometers. Kind of really ridiculous, and the devices are tens of nanometers. But there's something else we have to think about. And so one of the new kids on the block, totally unproven, and you can never underestimate what silicon will do, CMOS technology, just as you should never underestimate what silicon photocells do. But nevertheless, people are beginning to look hard at ferroelectric materials. So why is it better? If you consider, just say, start with memory. Memory in computers these days, like RAM, is you have a capacitor, you charge it, but it's leaky. So you have a little transistor that continually, every, tens of milliseconds, puts on a little juice and recharges the capacitor. In ferroelectrics, what you use electricity to flip a spin. And then once you flip the spin, it's done. So it's like the old magnetic core memories, a little current, you magnetize it, no more energy. And so the first application would be DRAM, but it's also possible to design logic circuits using ferroelectrics. And the hope is that you can get down to 100 millivolts. The KT is a 40th of an EV. And so 5 KT, you can go, but you need a little bit higher because you want the reliability of hundreds of billions of these devices. But still, there's a real possibility you can get down by an order of magnitude. You can it shrinks well, at least on paper. You just run it through the Xerox machine several times on shrink mode. So that's a joke. Ramesh is one of the leaders in this. He's a material scientist slash physicist that I met at Berkeley when I was lab director. He's a brilliant guy, so I brought him into government and made him in charge of the Solar Sunshine Program. And so after he left, he went back to Berkeley and started his invention of ferroelectric materials, and he co-founded a company called Kepler Compute. He has since become the provost of research at Rice University. And so whether this works or not, who knows, but it is a real possibility. And so, and that's one of many people in the Department of Energy that came to the department by me getting on the phone and calling him up and saying, you want to work for the government? He had just been elected to the National Academy of Engineering. He was in 43. And imagine you're there and you're a superstar, and why would you want to work for the government? And I got a whole bunch of people like that. Room at Jumder, same thing, call them up. Hey, Room, come join me. And dozens of people came that way. And you know, half of them said, no, I can't do this, but others said, and many of them commuted. Their families, in case of Arun and Ramesh, were at Berkeley. So it was a hard life. They would commute back and forth. And they would say, well, can you, every couple months, can I visit my family, and can the government pay for this? And I said, no. Because there was an unusual time where we obeyed laws. Anyway, okay, let me talk about energy storage. This is my favorite battery. Let me tell you how it works. When you have some intermittent energy, you do the energy intensive thing. And then after you've done the energy intensive thing, like pumping water from a well, you can use the water whenever you feel like it. And so it turns out that pumped storage, MGH, lifting mass up a hill, is 95% of all energy storage. If you have an existing dam, it is by far and away the least expensive way of storing energy. You think, how efficient can that be? You don't have a dam and you have a couple hundred feet and you pump water up the thing and there's losses and then you're up there and you let back down. And the answer is it's comparable to a flow battery. It can be 80% efficient if you're a couple hundred feet. And so since leaving Department of Energy, even when I was there, I was saying we've got to convince people that hydroelectric dams, once built, are not a bad thing. Please don't tear them down and put in turbines that can go both ways. When the time comes to replace the turbine. Let me talk about ordinary batteries. This is energy density. On the x-axis is energy per unit weight. On the y-axis, energy per unit volume. Energy per unit volume, crucial in cell phones. Energy per unit weight, crucial in anything that goes up in the air. And for mobile platforms like cars, you want both. This is where the Tesla battery is today, and there's where I think it will be. Pretty optimistic, time scale 10, maybe 15 years. Why 15 years and why it's not that optimistic? I'm on the board of Amprius and we're shipping samples that are of that energy density. But the lead time to get into cars is at least 6 years for many reasons, mostly safety reasons. Cost of batteries, great. Another learning curve. You know, I'm stressing learning curve, which is on a logarithmic pace, the cost goes down as you increase by a factor of 10, a factor of 10. You just get better at manufacturing. And in the process of manufacturing, lots of little innovations. Moore's law wasn't one big thing. It was lots of innovations continuously. And so there's no physical reason why it should be linear once you go into these sort of learning curves. There's no fundamental physics about this, but it happens in just about everything. from the cost of a Model T to solar to batteries. And the cost was fantastic. In very low-scale production, lithium-ion batteries were $2,000 a kilowatt hour, and 2020 they're less than 100 now. Manufacturing costs that OEMs like a GM would pay for a battery, and by 2030 they're saying probably $50. At $50, then this is directly related to the cost of the electric vehicle. And the electric vehicles have to be less than internal combustion engine without subsidy. They can't be equal, they have to be less for a couple of reasons. There's inertia, and there's another very important reason. People are afraid of charging. Their charging time, if it's several hours, no good. If you're trying to do an interstate and you need even an hour to charge your battery to go 200 miles, no good. So about a decade ago, I started giving talks, and the goal was that you want the battery to last longer than the human bladder. What does that mean? It means while you're discharging, your battery's charging 4 or 5 minutes, everybody's happy. The gasoline stations are especially happy because they make more money selling you beer and potato chips than gasoline. Gasoline is a very slim margin. And so this is a real possibility, and that would be the final thing. And you don't want to tie up a charging station for a half an hour. The Tesla super fast charge is about a half an hour to go 150 miles. You don't want to do this. You really want a few minutes. And so this is a big goal, a lot of nanotechnology in making the batteries have high conductivity, okay? But also a resource issue, okay? I talked about copper. What about lithium? Again, you take a step back and say, where's lithium in the world? And the most material of solid material in the world is silicon. So this is oxygen, that's silicon, that's sodium, that's aluminum. Here's lithium. It's down by 1 order of magnitude, 2 orders of magnitude. Yeah. Here's nitrogen, and here's chlorine. It's not that rare. There's a lot of it. And so what it is a concentration issue, a mining issue, a refinement issue. And so our major sources of lithium today, there's ore, but there's also salty water that you pump out of the ground. You put salty lakes to let it evaporate, and you actually use chemical means to extract the lithium. Very high polluting, but any underground water you pump up has got all sorts of noxious stuff in it. In addition to that, it's doubly polluting because as you sink these water tables of salt water, the freshwater tables drop into the salt water, and you're depleting freshwater tables. And so is it possible to extract the lithium out of salt water, just the lithium, and throw the rest of it back into the ground? If you do that, it becomes non-polluting. And there's lots of salt water, lithium in salt water. In wells, when you drill for oil and gas, you find water. Sometimes the water is an order of magnitude or more produced water than oil. And so can you do that? And so we started thinking about that, and Chong Lu, as a postdoc co-directed by Eastway at Stanford and me, had the idea of having a half battery, iron phosphate, cheap stuff, and if you play some tricks, you can get, you're trying to mostly separate lithium from sodium. And so the lithium will intercalate better and faster than the sodium. And so at the beginning, you could get 2001 sodium to lithium to 95% lithium to sodium. And at University of Chicago, where she's a professor, she's now recently, you can start with seawater, 1 in 20,000, and you can get 81 lithium. So the issue is, can this become practical? We don't know, because it's a surface thing. And anything having to do with surfaces means you may or may not mass produce. But people are beginning to warm up to this idea, and people are beginning to actually extract out of salty water, pull out the lithium, and pump it down in the ground. And so I've been advising Shell for a while on how to make this transition, and I joked, you your produced water, the lithium is more valuable barrel for barrel than the oil. And I want to see the day where you're going around looking for salty water with lithium and you find oil and gas and pump it back in the ground, which is what they do with the salty water. Okay, so how do you improve the battery even further? Well, it's all been recognized if you have a metal anode, a pure metal anode, instead of lithium in graphite or lithium in a mixture of carbon and silicon, which you can have higher lithium to anode material. The other materials overhead, pure metal, no overhead, and the voltage actually increases. So what's the problem with a metal anode? The problem is if you have lithium metal and you run a charge too fast, you can have a little imperfection in the material, and that little imperfection, so the lithium has in the boundary layer between the metal and the electrolyte, there's a solid electrolyte interface. It's like an oxidation layer that self-protects, allows lithium to go for it. And so this SEI layer is a natural product and it's great. But if you charge too fast and there's a little bump in the lithium, then it's a feedback where the higher electric field draws more lithium onto here, and so you're making more SEI layer, which is using up lithium. But worse than that, this bump is, it just propagates. And so higher and higher electric field and the battery shorts. And so, really stupid idea. In addition to the naturally formed SEI layer, can you put in another layer? A lot of the battery research is to use different electrolytes that have a stronger SEI layer. But if you can have a higher Young's modulus that passes lithium with not much more resistance than this SEI layer, you're okay. And what we are doing is we're playing around with an SEI layer, and in this coin battery experiment, we have lithium metal and sulfur, and it runs for 300 cycles and then it dies. And for those of you who are experts in lithium sulfur batteries, you don't see this, you see a gradual decay. Now the reason it dies is if you do a postmortem on this battery is that there was a known chemical reaction of the sulfur with the lithium, and then when we opened up the battery, there was no more electrolyte. So now you can focus on an electrolyte that's just chemically stable. It doesn't have to be a stronger SEI layer. So it shortens the thing. So we think this is possible, but it's also possible for any metal anode battery. And in utility scale batteries, there's enough lithium for EVs for hundreds of years. You have 3 orders of magnitude for utility scale, not enough. And so you've got to use sodium, zinc, manganese, much more earth abundant stuff. But the batteries, normal aqueous battery solutions, you have to stay below hydrogen oxygen production. So you tiptoe around there. And and they also have a dendrite problem. And so what we think might happen, we haven't shown this yet, is that with this new two-dimensional material layer, it's keeping the sulfur from getting onto the metal anode. In an electrolyte, there's 2 lithiums and sulfur, 6 sulfurs, 8 sulfurs, down to 4, 2 sulfurs, and there's no sulfur. So the pores are so small that the sulfur is just kept where it should be kept. The hydration layer, if you have a positive ion aqueous solution, there's a water shell around it. And that too, it will be too big to get to the metal anode, so it strips away the hydration layer. That could be a big deal, because that means water doesn't come in contact with the electrode, which means you can go to higher voltage. Okay, yet to be shown, so I'll keep you posted. But these are some of the things that are possibilities. I should also say that we're going to still need some turn-on power. And I'm not going to talk about nuclear and natural gas. Maybe you can ask me questions. So there are other things. If you want to decrease the overhead in batteries, metal anodes decrease the overhead. But hey, why not forget about all the overhead of the anode and cathode and go directly to chemical fuels? hydrogen, green methane, things like that. A big deal. That's why there is so much attention on hydrogen. Hydrogen now comes from methane. You do a process which makes, in the end, methane and CO2, and they vent the CO2. So you're actually no better off than burning natural gas in terms of carbon pollution. There's blue hydrogen. You take the methane, you capture the carbon dioxide, and you sequester it underground somewhere. And these are, by the way, the cost of these things. And green hydrogen is the best because you're using clean energy. Why is it so much better than blue hydrogen? Because we found that when you drill for oil and natural gas, you're disturbing the ground and it leaks methane. It's not sloppy capture of methane in the well, it just kind of leaks. And it can be 2 to 4%, which is a lot of methane. So ultimately you want green hydrogen. Green hydrogen is going to be very good, or hydrogen, because you can use it to decarbonize steel, plastics, chemicals, fertilizer, stuff like that. The starting building block for aviation fuel, all good. Problem, hydrogen is very leaky. Much more leaky than natural gas. It diffuses through a lot of things. It makes steel pipes brittle as well, and so you can't use any steel existing infrastructure, and so it has to be plastic lined or something. Other big problem, the way we detect hydrogen is through mass spec. There's a very high intensity Raman way of doing it, but you need remote sensing, because it was only with remote sensing we figured out that there's a lot more methane leaking. And why are we concerned about hydrogen leaking? Because if it leaks into the atmosphere, it keeps methane in the atmosphere longer. And this is now accepted as, if you go to a partial hydrogen economy, it will be a very big deal. So if you want to think about something, think about getting remote sensing for hydrogen. Either tiny mass specs on a drone or high intensity cheap lasers, Raman scattering. Okay. Another problem with hydrogen, no pipeline. Remember, can't have a pipeline until you get leak detection. So what do you do? And so how do we move hydrogen around now? We put it in steel tanks and truck it. Not good. And so there's a new opportunity that people have realized, and that is, why don't you send the energy by electricity to a fuel cell, and remember, fuel cells take hydrogen and they make electricity for vehicles, just run it in reverse. And so electricity makes hydrogen. But the good thing about that is you make hydrogen at the site, at the oil refinery, at the steel plant where you want it, so you don't have to truck it. And so another Department of Energy alum, when I was there, Ravi Pasha, he became Associate Director of LBNL, and then he was recruited with $1 million+ salary to join Bloom Energy, because Bloom Energy was working for more than a decade on solid oxide fuel cells. And he was very excited a couple months ago. He said, Steve, this is wonderful. We've got 88.5% efficiency, electricity, hydrogen back. One way, okay? Which is really good. Now you say, well, these things work at high temperature, but temperature is not an issue. Temperature scales very nicely. You just make it bigger, and the petrochemical industry, the Haber-Bosch process knows about that. So it could be very exciting that you just send electricity by wire and make the hydrogen where you want it. And so it could be a source of decarbonizing things. Ultimately, what you really want is to take the combustion products. I get a crank phone call literally every 5 minutes. It's junk robocalls. I say, are you there? And I say, are you a robot? And they hang up. Anyway, CO2, and you have to import energy because it's going uphill because you're burning some, let's say, carbon-based something, and so whatever process, you have to input energy. First targets would be hydrogen and CO, but ultimately you want to make a liquid fuel at room temperature. Very, very important, because liquid fuels at room temperature can be put on tankers. And so here's a little quiz. Here's a super tanker, and you ask, how much does it cost to ship and store oil anywhere halfway around the world? In terms of dollars per gallon, well, it's not, cost of gasoline is wholesales $2.50 or something like that. The answer is 2 cents. It's free, nearly free. Not really free because they use high sulfur fuels and things like that. But shipping by a tanker is really cheap. And so think of these things as transcontinental transmission lines. You can go across the Pacific and the Atlantic. And so that is the ultimate goal of liquid fuels. And for airplanes, you really want liquid hydrocarbon fuels. Okay, now, I guess I'll talk a little bit briefly about utility scale stuff. Chances are natural gas is CCS or fission or fusion, let's say fission. The main problem with fission is we don't know how to build reactors on budget, on time, and they're nowhere close to being economically competitive. If we learn how to do what we learned before 3 Mile Island and build very safe reactors, it is possible. In terms of safety, in terms of deaths per terawatt hour, coal, anything combusting, coal, brown coal, coal, oil, even biomass. Where's nuclear in here? It is about a factor of 100 safer than burning wood pellets. It's a little safer than wind, a little more dangerous than solar, but in the dangers, why is wind dangerous? Because they can fall off towers. Why is solar dangerous? Because they can fall off roofs. Why is nuclear dangerous? Because if you have a contamination leak, it can give you cancer. Okay? So it's not that dangerous, but it's really the economics. Spent fuel, new technologies, boreholes this big. You can go down a couple of kilometers, so it's storage without having people and trucks, and so that's a possibility, but it's the economics. Fusion, I'm not going to go into it, but the estimate of deployment of commercial fusion is somewhere between 40 years and never. Commercial, not a scientific. This is shared by Omar Hurricane, who I've gotten to know over the years, who is the guy who made the NIF fusion work. He doesn't think it will ever become commercial for many, many reasons. Anyway, okay, let's talk about agriculture. I know I'm running out, but so in my next hour, I'll try to go a little faster. You're going to be safe at 4:15 or 4:30. I got to catch a plane. Okay, so let me talk a little bit about history. This is a record of temperature using oxygen as a proxy for temperature, going back, present time, going back in time, present warm period, ice age, warm period, ice age, warm period. And then what happened? Agriculture started about 12,000 years ago. And it started, or 10,000 years ago, it started when the climate stabilized. And it didn't start in just one place, like Tigris-Euphrates area. It started in 5 places around the world. It was that, because people were smart in a lot of places around the world, Homo sapiens. And so when the climate stabilizes, you can actually grow food, and you have excess wealth production, and so you can have kings and physicists, which... because anyway, so this is a big deal, and we've had 3 agricultural revolutions. The first one was the domestication of wheat, rice, cattle, chickens, yeast, first irrigation. This was all at this time scale, very important. How do you turn grains and fruit into booze? This is from Robert Vogel, a Nobel Prize economist, view of history. And he says right here, the influx turning point, second agricultural revolution, that provided enough excess wealth to actually develop the agricultural revolution. And he talks about the beginning of the Industrial Revolution, wide engine, railroads, germ theory, blah, blah, blah. Okay? The second agricultural revolution is really amazing because it wasn't technology, it was policy. starting in Great Britain, they allowed people to fence their land so no one else could use it. And so there was no longer overgrazing and things like that. They made it easier to ship goods without stupid rules and tariffs and things like that. So policy is important. Third agricultural revolution, I mentioned it already, the Haber-Bosch process, the invention of artificial fertilizers from nitrogen and ultimately from the air. And they really enabled enough wealth creation, people didn't starve. Got Haber a Nobel Prize in 1918 for his work with Bosch. And then they realized it's a big deal, so they decided they were going to invent a reason to give Bosch a Nobel Prize in 1931 for high temperature, high pressure catalysis, which was the original Haber-Bosch process. But it was a big enough deal. Crossbreeding of plants to make them more productive. Norman Borlaug, well-deserved Nobel Prize in Peace for inventing dwarf strains of wheat and rice. So you have crossbreeding of plants and grains, you have fertilizer. And so from 1961 to 2021, this is the amount of land put under grain production around the world, flat. Even though we went from 3 to nearly 8 billion people, cereal production tripled. Real revolution. But there's greenhouse gas emissions. Beef burp a lot of methane, and so there's a penalty for the beef, and cows also. And you go down the list of things. That's beef. Poultry is 10 times less greenhouse gas than beef, because chickens don't burp. And now, if all the dairy cattle around the world and the beef we eat were a country, where would this in greenhouse gas emissions? It would be more than the EU plus Great Britain, and it would be more than the United States. So it's significant. Also, just in case you're interested, if you take all the animals we eat and our human mass and put them on one side of the scale and every other mammal on the other side of the scale, we're 96% of mammal mass. So we've geoengineered the world. So when I hear about we don't want to do geoengineering, come on, give me a break. Half the arable land is agricultural production. How do you get rid of the fertilizer? Because fertilizer makes N2O, and so there's a technology that says if you mix microbes with plants, stimulated by legumes who have a natural relationship, and so they don't need as much or really no fertilizer. So there's a company called Pivot Bio in the Bay Area that's developed microbes to do this. So the microbes are planted with the corn, very fertilizer intensive, and they're sitting in the boundary of the roots to the soil, and when the plant says, feed me, the microbes say, okay. That was from Little Shop of Horrors. I don't know, you guys. And so on the right is the microbial stuff, on the left is corn. It works, except it only partially works. You still need half the fertilizer, and different soils have different microbial environments. So you got to do this for different soils, but it took like 8+ years to develop this. And so that's a problem. Synthetic biology is great, but it takes too long. I was on the board of directors of a company that did the genetic engineering for Pivot Bio called Zymergen, and it took so long it went bankrupt. It got bought up by Ginkgo Bioworks, and the part of the issue was the long period of time it takes. This is not directed evolution, a la Francis Arnold, boom, and instantly you do 50,000 experiments all at once. So what you'd like to do is thousands and thousands of experiments all at once and put them in different cells, plants, and then see what happens. But Zymergen had to put in one gene, one promoter at a time. And the solution was 12 genes. It takes forever. And so you really want to put in dozens of genes, which means big DNA, 50 kilobases, 100 kilobases, which you can't do. And so again, so I said, so I'm working on that. We think we have a way. And so of getting many, many genes in. Okay. Now, carbon capture. We're going to go over 450 for sure. We're probably going to go over 550. So you need carbon capture, but the cost is prohibitive. Air capture is over $300 a ton. Capture from a power plant, about 100, maybe a little less. And so here's another problem. We emit 42 gigatons carbon dioxide equivalent. Agriculture will take decades, and other things, aviation fuels, take, to make them economically competitive. So you anticipate 10 to 20 gigatons of carbon capture per year. So let's think of the scale of 10 to 20 gigatons. Well, that's a lot. If you pump carbon dioxide into the earth at very, very high pressure, you can get it to become superfluid with a density approaching 1. But what is 10 gigatons? We'll compare it to what other things? We have a lot of waste, solid waste, garbage dumps. 2 billion tons of solid landfill waste a year compared to 10 billion. But the density is 2 or 3 or 4 times less. So the volume is an order of magnitude more per year. This is non-trivial. So anyone out there, you've got to think of a way of getting this. The sheer volume is enormous. But in the end, I think whether it's an artificial method, and I'm doing something, I know people at Caltech are doing novel ways of carbon capture, but once you've captured it, you've got to figure out what to do with it. And you've got to get your capture costs down by factors of 3, 4, okay? So I think that will happen, but the volume thing is an issue. But in the end, photosynthesis is great carbon capture. Most of the biomass gets recycled. We don't eat it. It just goes back into the carbon dioxide thing. So this is important. So let me show you another way of carbon capture for a moment. It's really novel. It's a new material. It has to do with nano, because if you look at the material up close, the molecular scale, it's nano. It's called wood. Remember, that was on the list of things on a massive scale. Most of the buildings we build are less than 5 or 10 stories tall. And so think of building wood structures. Instead of steel and concrete, make them out of wood. Wood laminates, wood, because the big trees are gone. It's like the big fish are gone. And so wood laminates. And this is an example of a 20-story tall building. But in the US, I think it's 10 stories now. Is allowed. This is an oat milk company in Sweden called Oatly. And so wood, now, you want to make the wood, the buildings, the exterior construction of the buildings last not 50 years or 100 years. You want to make them last 500 years, 1,000 years. Is that possible? Yes. Old London are wooden buildings, 1,000 years old. Okay? So just remember how to build wood and wood laminates. And now you get to sequester carbon, so you grow a forest, use the wood, grow another forest, use the wood. If it's 500 years, that's pretty good. That's better than a forest. And it displaces carbon-intensive materials. And so a little policy that rewards wood buildings and penalizes carbon-intensive materials will get people to decarbonize steel and concrete. Concrete you need for foundations. Wood doesn't do well underground. Well, actually, it can do well. That's a different story. I won't go into it. But anyway, wood, so the invention is wood. And then how long will it take to make this transition? So you look historically at this, Energy Department agent branch of the Department of Energy. We're wood, we transition to coal. You see this, there's rise and fall. This is every 50 years, so this is a century. Then we go to oil and natural gas, and you see nuclear, hydrogen, and other things. And so, it looks like it takes about 60 years, roughly, full with half max to transition. It takes a long time. It's actually worse than that. Put on a different scale, transition from coal to oil to them. We didn't get rid of the coal, we just added. Okay? So what we're asking for, remember, 0 emissions by 2050. And so we've got to break this. So the scenario is we're on a collision path for 3 degrees. And I use this analogy once or twice in the Department of Energy. I was told you can't do this. I liken it to a ship heading for an iceberg. And I called it Titanic the sequel. And off in the distance you see an iceberg. Nah, it's not there. No, it's there. Nah, it's not there. And then it's there, and it's too late. It takes a half a century at least to turn the ship. So that's where we're heading. Now, I know you're looking nervous. You're not nervous? Okay. Now I'm going to address the fundamental problem. The fundamental problem is population growth. All the innovations allowed us to grow the population. Okay? So we're tootling along less than 1 million people, a third of a million in a million years, and then boom, it starts going up. This is a science article on population. They estimated 13 years when it was published. It didn't take 13 years. It took a couple of years less. Now, the interesting thing about population is across all societies, as you get to be middle class, you have fewer kids. Many, many reasons. Women's education. Infant mortality goes down. If you had, before you needed 6 kids to have 3 survive to take care of you in old age. And so the families go small and small and smaller naturally. And the economists say, you don't want to do this. You want them to make more people. Okay? And let's go into this. So here's populations. The gray is record. Red is projection. And you look, China is going to plunge in population. You know, one-child policy you get rid of. You want to encourage people. They're still having 0, 1 kid, 2 kids max. But you want to look at Japan. It was leading since 1900s. It was decreasing population. So what can you do about this? And what is Japan doing? So part of having kids is and grandkids is you want them to take care of you when you're old. And so, but let's talk about economics. Increased economic prosperity in all countries is based on having more younger workers to produce a smaller aging population. Where I come from, that's called a Ponzi scheme. Okay? More early investors to pay off more late investors to pay off the early investors. Okay? And this is crazy. It's really unsustainable. And so, and we have these revolutions that transition from mechanized farming to fewer farmers. They go to the cities, they make stuff, washing machines, cars, and other things. But now that's being automated, so then what do? You want meaningful jobs. And so there's an opportunity to give people meaningful jobs in a very highly efficient automated society. In terms of older people, but it's artificial intelligence, so you can get Alexa to talk back to you, and you can, and during experiments of, your parents, if you're, have a job, you can't spend 5 hours a day talking to your parents. You don't mind talking to them if you're really a good son or daughter, a half an hour a day, or a half an hour a week, but not 5 hours a day. So you can get a robot to talk to you, and the robot is answering you, and you can make it sound like you. It's not fraud, you say, no, because the robot will download to you what transpired, and they can give you the condensed version. And so, and people have warmed up to this. You've probably heard stories of people getting friendly with Alexa. But in the end, the driver of the economy is GDP. GDP means you make more stuff, you throw it away, and you make more stuff. You increase the GDP by building a building, tearing it down 50 years, and building another building, even though it doesn't make any sense for congestion, resources, anything. And so let's think of what do we really care about. Is it really GDP? Well, yes. But after a certain level, you care less about it. And so if you become middle class, it's not that big a deal unless you have some ego problem. And so what do we care about? We care that our families and children are safe. We can send them out and play in the street or in playgrounds. They're going to be safe. Your country won't be attacked from hostile takeover. You want to be healthy in old age. You want to be emotionally connected to Alexa or whatever that then connects you to your children, the 1 or 2 or 0. And let me close by quoting what Robert Kennedy Sr., not the other Robert Kennedy, and he said, the gross national product does not allow for the health of our children, does not allow for the health of our children, the quality of their education, or the joy of their play. It does not include the beauty of our poetry or the strength of our marriages, the intelligence of our public debate, or the integrity of our public officials. It measures neither our wit nor our courage, neither our wisdom nor our learning, neither our compassion nor our devotion to our country. It measures everything, in short, except which makes life worthwhile. Thank you. Yeah.
So Steve is agreeable to answering
A couple questions. I don't know, whoever my host is won my card.
It's waiting for you, but there's a few minutes. So
Okay, 10 minutes, fine. Okay, fine, okay.
a couple of questions. Who would like to? Go ahead.
So maybe you can know a little about the other side of this problem. Is we heard a lot about actually oil running out of peak oil maybe 20 years ago, but now we hear a lot less about it. Is that an issue?
Not an issue. Our ability to find the question was, I heard a lot about peak oil, we're going to run out of oil, it's maybe self-correcting, is that still an issue? No, the peak oil that occurred in the United States is they found other resources cheap in the world. But meanwhile, technology of finding and recovering oil has really improved remarkably, almost as fast as renewable energy. And so there's an abundance, and natural gas was a byproduct. And for the first time, you can begin to prospect for it and recover it. Used to be poke a hole in the ground, 5% oil. Now, with good recovery, 50% is expected. So the oil reservoirs will go up by a factor 10. The ability to find it, deep water drilling has improved a lot. And so the technology of recovering oil and natural gas has really improved. So I don't see it in hundreds of years, at least 100 years, but probably hundreds. There's too much. If we extract a small fraction of what we can find economically, we're cooked.
Questions?
We may be cooked anyway.
Go ahead.
So what do you do to take into account disasters like major fires or other things that create huge pollutants that are perturbations to the environment? So how would you imagine taking that into account? It kind of relates to your use of wood because
Right. So the question was, there are major fires, and in major fires, you're unsequestering the carbon dioxide from forests and also large particulate matter that has huge health hazards. And so that's has a big impact. Rising temperatures, more methane seen leaking out of tundras and other places. We don't really know if there will be a nonlinear tipping point, when it will occur. Also, the carbon dioxide and methane stored in off-shelf ice formations. Don't know anything about that. So these are all things that are largely unknown dangers of how to be really quantitative. But for sure, if you look over the last couple of decades, the number of forest fires has gone up. And this is an issue. So we're just, it's bad stuff.
Okay, one more back in the back. Yep.
Going back to the slide about producing hydrogen at the site,
Yes.
how is that natural gas going from the extraction point to the industrial site?
No, ideally, I'm stressing you want clean energy. Yeah, you want clean energy to go by wire to produce hydrogen, which has a lot of clean energy benefits, so you get rid of the transportation part. But I stress, in the end, you don't want natural gas and storage because of the methane leaks in the recovery of natural gas is an issue, okay? And so, because you poke holes in the ground, it leaks. One last question, I guess.
Question here. Good.
So you just mentioned that there's maybe hundreds of years of
Possibly,
oil in the ground.
yeah.
How do we incentivize not using oil any longer?
The best way is to make the alternative cheaper and better. I started to quote Sheikh Imani when I was Secretary of Energy, and people, it's very important, he said, the Stone Age did not come to an end for lack of stones. And the oil age will not come to an end for lack of oil. Now, what he meant by that is, in the Stone Age, you transition to better solutions, Metal Ages. And if you transition to better solutions for energy, and energy is great, it lifts, it transforms the world. And so if you transition to better solutions of energy that are cleaner, that aren't going to do this to the environment, then you're okay. So that's why renewables plus all the infrastructure to use renewables, like energy storage, are the incentive. Because energy is about money, at the bottom line. And if you want to quadruple or double energy prices, it's not good. If you transition in a clumsy way, German energy transition is a clumsy way, shut down existing operating nuclear reactors, stuff like that, you drive up energy prices. And then when you drive up energy prices locally, the companies move to places where there's cheaper energy. And so Germany's beginning to see this. They're offshoring. So in the end, better solutions, okay? And so as a technologist, I'm fully in favor. You give them better solutions, it becomes less political, right? And, why, if an electric vehicle costs $20,000, the maintenance is Zippo compared to that, and the battery lasts longer than the bladder, why would you not buy an electric vehicle? Right? Lots of questions.
So you mentioned energy is about money, which I think is the real key. If the goal is to have zero carbon by mid-century, so I guess like 30 years, and if we ask, has there been examples in the past where we can deploy technologies at such a scale, at such a speed? And I can only think of two. The first example is the internet. I'll just talk about the first example of the internet, where we transition over, let's say, 2 to 3 decades, since the 90s or so, that completely changed everything. And it's mostly driven by private sector. And then you ask, why would that happen? Well, there's a lot of, because the transition is extremely profitable.
Not profitable, it doesn't require a change in main infrastructure, and it replaces something, and it's so cheap. Yes. Anything with compute and everything, but if you look at real infrastructure changes and look around, and real infrastructure is longer, much longer, right?
Yes. So my question is that there exist huge markets before the internet transition, say the retail, the advertisement, all of that just moved to the internet, and that transition is extremely profitable. And then you have new industries and so on. Now, if you look at energy transition, it's not very clear where the profit will come from. So EV, for example, is a large automobile industry that hopefully will transition to the new. But then, other than that, are there very profitable transitions that can drive that?
Yeah. So yes, in principle. So the comment was. There were very rapid transitions. The internet was one example. Telephones and everything that is a little bit different, but transition from landlines to cell phones very rapid. Get another crank robocall, and so there are a few, mostly in electronics and communications, that were very, very fast. And so that's great, but then the massive infrastructure stuff seems to be slower. And now, what's the profit? The profit is, I was pretty optimistic about this. Where is it? Suppose solar energy drops another factor 2, which is likely. Even silicon solar energy likely drop a factor 2. So it's now cheaper at levelized costs than natural gas. Okay, so make it twice as inexpensive, and make the energy storage issue, solvable at an economic price, right? Then the profit is hey, it's cheaper. And it's still about money.
Whether that can happen at the speed that is required.
Right now, it's efficiency is better. You want efficiency because of land use. You want all the other energy storage issues, the transmission issues, and then it takes care of itself. But you need those other bits and pieces to get to 89. Now, you still need 10, depending where you live. In your Northern Europe and seasonal, you can't be 80% renewable. So it depends on where you live. So you still need turn on or shipping. Remember oil tanker? So you go to really cheap places and then you ship. And then it becomes feasible again because that's what we do. Oil was cheap and we ship it around the world. And so it's going to be the same. Suppose we have the technology to make liquid hydrocarbon carriers. It's problem solved. So I partially remain hopeful, but the other part of me says that most of the world doesn't realize it takes a half a century to turn the ship. Thank you.
Thank you so much.